Hello everyone, it is a pleasure to be back at the SEAPAVAA conference in person. It has been too long since the Bangkok meeting in 2018. I would like to thank the organizer for giving me the opportunity to present this project. This work has been carried out in the framework of European collaboration between various laboratories, archives, and companies located in France, UK, Germany, Portugal, Poland, Bulgaria, Spain, Italy, Austria, Ireland, and Czech Republic. The European Commission funded this joint research project entitled Mnemosyne, and it was a 4-year project dedicated to the preservation of film heritage and devoted to alternative storage techniques. As you know, the international standard recommendation for archiving cellulose triacetate films over long periods of time, more than 100 years, is to store them in a cold room at a temperature below 10 degrees or even below 0 degrees Celsius. This method has proven to be very efficient for the preservation of photographic and movie films heritage and has allowed to extend the life expectancy of acetate films. However, today it raises questions about its carbon footprint, because in most cases the operation of the cold storage facility requires fossil energy, and the running costs are getting higher too, nor affordable for archival institutions. It has become necessary to find compromises or greener strategies. We therefore looked for introducing more passive systems for the conservation of movie film heritage. When I began working in the field of photograph preservation in the 1980s, it seemed that the problem of preserving motion picture films was solved with the use of cellulose acetate base instead of the flammable cellulose nitrate base. In 1981, Eastman Kodak Company announced a life expectancy of 300 years for cellulose acetate films. However, in some countries with tropical climates, archivists were already seeing, or I should say rather smelling, the decomposition of cellulose acetate, what our community will call the vinegar syndrome. These early warnings were confirmed by Michel Edge in a series of scientific papers in the late 1980s. In the following years, growing numbers of heritage institutions reported the occurrence of vinegar syndrome in their collection. Finally, the Image Permanence Institute demonstrated through extensive study the short life expectancy of cellulose triacetate. Also, it was not flammable. Its lifespan could be less than that of cellulose nitrate films. And these studies conducted by Peter Adelstein and Jean-Louis Bigaudin highlighted the impact of temperature and humidity on degradation and the autocatalysis phenomenon. That is to say that acetic acid produced during the acetate-base hydrolysis accelerates the degradation process. Then several options were possible to slow down the film degradations. In addition to storing the film in a cold and dry environment, as I mentioned before, another strategy was to trap the acids emitted by the film base during its decay. In 1993, the Kodak company introduced the use of zeolite, known as molecular sieves. These zeolites are very porous aluminosilicates which can trap acid molecules in their pores. Kodak filed a patent in 1993, and these zeolites were made available shaped in beads in Tyvek bags to put around the film reel in the can. Kodak company recommends around 37 grams for 300 meter of 35 millimeter films to be renewed every 2 years for storage at room temperature. A few years later, the Fujifilm company introduced on the market its own zeolite, aluminum hydrotalcite, under the name of Keepwell. They were packaged as patches to be placed on the surface of the reel. I am not sure if Fujifilm company still produces Keepwell, but similar products are marketed today by the Japanese company Imagica, either in the form of patches or in the form of small bags filled with zeolites. Those zeolites can absorb some acetic acid, however, it absorbs more moisture, more water than acetic acid. It is effective, but the improvement in preservation is mainly due to the absorption of moisture rather than the removal of acetic acid. Then, within the framework of the Nemosine project, we try to develop and test other adsorbents more efficient and more selective for acetic acid than zeolite. The first step of this research was to determine what are the VOCs emitted by a film and their emission rate, because it was important to identify any VOCs that might compete with acetic acid in a scavenging process. It was also necessary to find out whether these other volatile compounds emitted by the acetate base could interfere with a specific sensor for acetic acid that was planned to be developed and introduced in this project. To identify the VOC emitted by a film and their quantity, we use relatively recent methods of analysis called the PTRMS, acronym for Proton Transfer Reaction Mass Spectrometry. This technique allows for the real-time qualitative and quantitative assessment of VOCs present at ultra-trace levels, from parts per trillion ppt to parts per billion ppb. It is highly sensitive. If you approach a bottle, it may tell you what is inside without opening it. For our test, the French Film Archives provided us with 41 cellulose acetate films, 35 mm in black and white or color, and of different brands, different degradation level dating from the 1970s to the 1990s. To be analyzed, the film is placed in a Teflon chamber. Air is sucked in from this chamber and introduced into the PTRMS, where the chemicals products emitted from the film base are combined with protons to form ions that are separated and analyzed by a mass spectrometer. We identify over 121 different VOCs emitted from these cellulose acetate movie films, and those emissions were stable over more than 10 minutes. These compounds are either degradation products, residues, or additives from the motion picture film. Among this huge variety of products, acetic acid, acetaldehyde, acetone, butanol, dimethylformamide, formic acid, methanol, and propanoic acid are the most commonly found. Acetic acid is not always the most abundant VOC in the film cans we analyze. In 3 cans, we found mainly dimethylformamide, in 6 other mainly butanol, in 2 mainly acetaldehyde, and for 2 mainly formic acid. The emission rates reach more than 10 ppb of acetic acid or dimethylformamide per second. Those results were very interesting since we did not expect such a variety of compounds in film can and such emission rates. Thus, the compounds to be neutralized were mainly acetic acid and some formic acid and propanoic acid. The other compounds should not speed up the film degradation but may pose health and safety issues. To trap acetic acid and other acids, we tested a new kind of porous material, the metal organic framework, or MOFs, that have been introduced around 20 years ago. MOFs are crystallized porous solids synthesized in the laboratory by linking metal ions with organic molecules. There is a very large number of possible combinations of linkers and metals that leads to a wide range of structures with tunable pore size and polarity suitable for the selective absorption of gases. At present, over 90,000 MOFs have been synthesized, and it is hoped to use them for CO2 trapping, but they have proven to be interesting in many other fields such as air quality, gas separation, and biomedicine as drug delivery. In our project, several of these compounds were synthesized and evaluated for their efficiency in scavenging acetic acid in film cans. Thanks to our partners of the Institute of Porous Materials, we selected a MOF named 1100 that meet our expectations. This compound has many advantages. It is cheap. It can be produced by a green synthesis at room temperature. Acetic acid absorbs strongly to metal sites, and there is little risk of release. Laboratory tests have shown that this 1100 MOF outperforms zeolites and other porous materials, not only for acetic acid but also for formic acid and some other VOCs. Thus, we decided to test these MOFs in film archives. We filled a Tyvek bag with 150 grams of 1100, and these bags were sent to film archives, the Deutsches Film Institute, the Austrian Academy of Science, and the Institute Valencia de Cultura in Spain. The films selected for this test had an acidity level around 1 to 1.5 on the ADES-TRIP scale. That is to say, an acetic acid level in the range of 1 to 5 ppm. The MOF bags were inserted into a specially designed box lid manufactured by Acumplast company. There was also a space on the side that allowed a sensor to be placed near the film in order to monitor continuously online the acetic acid concentration in the film can. This sensor was developed by our partner Biosensor in the framework of the project. I present here the test made in the film archives in Valencia on a black and white negative film with optical sound entitled Un military medio, dated 1959, and we measure the acid concentration in the can. The average was around 2.2 ppm. Then we added the lid containing the MOF bags, and the acid concentration drops quickly from 2.2 ppm to 0.3 ppm on average, and remains at that level for at least 1 month. Unfortunately, the delay due to the pandemic did not allow us to continue the experiment for longer periods and then to determine when our adsorbent would be saturated. However, according to the theoretical model that my colleague Abi Motar from the University of Lisbon has established, it should stay efficient for a few years and significantly slow down the acetate degradation process. Keeping 10 years a fresh 2 kilo cellulose acetate film at 22 degrees at 40% relative humidity with 100 grams of MOF 1100 produces the same benefit as keeping it at 5 degrees Celsius for 10 years without MOF. If the film is already degraded at a strips ranking of 1, the amount of MOF should be double. That is to say, having 200 grams of MOF in the film can at 22 degrees Celsius, 40% relative humidity, will produce the same benefit as storing it at 5 degrees Celsius. However, there was still one aspect that we wanted to improve, the shaping of MOF. MOF is produced as a powder and the usual shaping is in the form of granules or beads that are not very convenient to handle and use in film archives. I have therefore proposed an alternative solution which consists of incorporating these MOFs powder into sheets of paper. Paper sheets are easy to store, to handle, to cut to box size. However, introducing a large quantity of an inorganic filler such as a MOF in cellulosic fiber is not easy because beyond certain quantities the paper sheet becomes extremely brittle. I therefore mixed the long cellulose fibers used to produce paper sheets with nanocellulose. The nanocellulose will disperse between the MOF particles and ensure a better cohesion of all the components of the composite. Thus, it was possible to produce membrane with more than 70% of MOF, which remained quite flexible. In collaboration with the conservators of the National Archives, we produced 20 by 30 centimeters sheets of this MOF paper. Our PhD students, Pierre Tignol, tested, characterized, and optimized the property of these composite materials. This shaping does not modify the absorbing properties of the MOF, which keeps all its characteristics. Finally, to ensure that these new materials would not damage the motion picture films or any photographic material, we applied the photographic activity test. Our MOF paper sheet passed this photo activity test. So far, these MOF paper sheets gave promising results for trapping irreversibly the organic acids, and it appears to be a very promising way to extend the life expectancy of acetate movie film in the context of sustainability. However, it may not extend the life expectancy of the dyes in color chromogenic films or nitrate-based films. These MOFs and MOF membranes prototypes can find other applications than cellulose acetate film preservations, in particular to protect archival documents or acid-sensitive museum objects. A patent has been filed and we are currently looking for industrial partners to bring this product to market. To conclude, I would like to thank the European Commission for supporting this Nemozyme project and all the project partners, my colleague of the Institute of Porous Materials of Paris, the Research Center on Conservation, the University of Lisbon, the Institut Valencia de Cultura, the Austrian Academy of Science, and Nadja Velaskovit, the French National Archives, the French Film Archives, Biosensor, and Plast. Thank you for your attention.